So it is time to enter into the frequency domain, right? In the analog domain, that is in continuous time domain, there are various kinds of transforms which takes the variable small t. This is the time variable to the frequency variable. Okay, it can be omega. Okay, so if it is a continuous time Fourier transform, or in the continuous time Fourier transform, this omega is the frequency, right? In case in the if you are taking s, this is the complex variable. So complex variable if it is Laplace transform. Okay, so t to omega in continuous time Fourier transform, and then t to complex frequency small s in the case of Laplace transform. So in the digital signal domain, the discrete time Fourier transform, in the continuous time domain we had continuous time Fourier transform. In the digital signal domain we have discrete time Fourier transform. DTFT is the most important transform. One can look at, and the corresponding transform of Laplace transform is the so-called Z transform. Okay, so these two are in the continuous time, and Z transform and discrete time transform in the discrete domain. Okay, so CTFT, this side we have DTFT, Laplace transform, here we have Z transform. That's it. Okay, these two are for continuous time and these two are for discrete time. So similar to here n becomes something called x of e raised to j omega for dt ft, and then n becomes small z in the case of Z transform. Okay, so we will talk both. We will discuss discrete time Fourier transform, and then we will discuss the Z transform. But it is important to recognize that the discrete time Fourier transform, sometimes people used to call Fourier transform simply. Okay, but we will stick on to this notation, discrete time Fourier transform. Later on we are going to study something called DFT, discrete Fourier transform. Both are different. DTFT is completely different from DFT, discrete Fourier transform. We will discuss. Okay, and this DTFT and DFT, they are very close to each other, but they are different. And this DFT is discrete Fourier transform. Okay, so DFT is something else. We will define at a later date. Okay, now let us jump on to the definition. The continuous time Fourier transform of an analog signal x of t is defined as x of t. If you take continuous time Fourier transform, then you'll get x of j omega. By definition, this will be equal to integral of x of t times e raised to minus j omega t and dt. Okay, and the limit is from minus infinity to plus infinity. And look at the small omega. Okay, the small omega is the symbol we reserved for normalized digital frequency. Okay, so don't confuse. In continuous time Fourier transform, the small omega is the analog frequency. But in discrete time Fourier transform, the small omega denotes normalized digital frequency. Normalized digital frequency. Okay, in continuous time Fourier transform, we have integration. But in discrete time Fourier transform, we will be having summation because it is discrete, right? So we will be using summation. Therefore, in digital signal domain, the DTFT of a sequence x of n is very simply defined as follows. Okay, before that let me define it and then later I'll come back to the notation. So discrete time Fourier transform of x of n is defined. I'll put the triangle symbol. This triangle symbol denotes definition. Defined as I said, integration is replaced by summation x of n multiplied by e to the minus jn omega, and this omega is normalized digital frequency. Normalized digital frequency. And of course the limit is from n is equal to minus infinity to plus infinity. But in this integration, this one is analog frequency. Even though we use same notation, but the meaning is different based on the context. Okay, and here the limit, here n goes in general from minus infinity to plus infinity. So this is the definition of DTFT. And if we expand it, it is a polynomial in e raised to j omega, right? If you expand this right hand side, what will you get? You'll get like this, like x of minus infinity times e to the minus minus into minus plus j infinity omega plus dot 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 plus x of minus 1 e raised to j omega plus x of 0 times e raised to j times 0 omega plus x of 1 times e raised to minus j omega plus x of 2 times e raised to minus j2 omega plus dot dot dot. Now look at this expansion. The Fourier transform of x of n contains a polynomial. Okay, so this is a polynomial in e raised to j omega. Okay, it is actually a polynomial in e raised to minus j omega or plus j omega. Because it is a polynomial in e raised to j omega, the symbol that is used for it is, instead of calling like this, we will call this guy as x of e raised to j omega. Okay, because on the right hand side I have a polynomial in e raised to j omega, so I will denote this DTFT of x of n as a capital X of e to the j omega. Therefore this will be equal to summation of x of n multiplied by e to the minus j n omega, and the limit is from minus infinity to plus infinity. And now if you look at this guy, this is a complex quantity. This is the complex quantity. Why is it complex quantity? Because I have e to the j omega. So this e to the j omega, see, I have e to the j omega here, right? So that e to the j omega I can write as cos omega plus j times sin omega. So I have a complex number, therefore the dtft of a real sequence x of n is a complex quantity. So whenever you have a complex quantity x of e raised to j omega, this guy has real part and imaginary part. Let me denote this real part by x suffix r plus the imaginary part by x suffix capital X suffix j. And this first one is real part and this one is imaginary part. So both real part and imaginary part are real quantities. Okay, xr is real and xj also real. Suppose if you write 5 plus j times 3, this 5 is a real number and 3 also a real number, but together is a complex number. That's it. Okay, so you have to multiply by j to make it imaginary. See, this xj is a real quantity. If you multiply by j, then the whole thing becomes imaginary. Okay. And here I did not write the argument. If you want, you can write. So instead of writing simply as xr and xj, you can write like this also. Nothing is wrong. X of e raised to j omega is equal to xr e to the j omega plus j times x of j e to the j omega. You can write like this also. Both are correct. This also correct and this also correct. And this is like, you know, a plus ib form, like a complex number form. Whenever you have a complex number, then you can write in terms of magnitude and phase. Therefore whenever you have the number like this, then it can be written as magnitude mod of r times e to the j times phase angle phi, right? So similarly, this x of j omega I can write as x of e raised to j omega is equal to magnitude of this guy and e to the j times phase angle of x of e to the j omega. That's it. So you can write x of e to the j omega and e to the j times some phase angle phi, and this guy I can write as m of omega plus e to the j times phi of omega. It's a function of omega, right? Phase angle is, therefore I can write function of omega. So this is another way of representing the discrete time Fourier transform of a given sequence x of n. Okay, so x of e to the j omega, by definition it is summation of x of n e to the minus j n omega, where n goes from minus infinity to plus infinity. Now this is a definition, right? Definition. Now if you look at the definition carefully, the definition says that x of j omega is a continuous function. What about the sequence x of n? X of n is a discrete signal. But x of e raised to j omega is a continuous function of omega. But the input is x of n. This is a discrete signal. and this discrete signal exists only at n is equal to 0, plus or minus 1, plus or minus 2, plus or minus 3, and so on and so forth. But in the frequency domain, it is a continuous function of omega. Time domain, you have discrete, but in the frequency domain, it is continuous. Please remember this for discrete time Fourier transform. Okay, it also shows that if omega is incremented or decreased by 2 pi or any integer multiple of 2 pi, then this function x of e raised to j omega does not change. Okay, so take this definition and substitute, replace omega by omega plus 2 pi, then the definition will not change. In case x of e raised to j omega, you replace omega by omega plus 2 pi, then in the right hand side you will be having x of n e to the j times n times omega is replaced by omega plus 2 pi minus n goes from minus infinity to plus infinity. Now what is this? In the right hand side, x of n e to the minus j n omega times e to the minus j n 2 pi. So what about this quantity? Here this n is an integer, right? So if you multiply 2 pi by an integer, again it is not going to change. So this will be always equal to 1. So summation of x of n e to the minus j n omega, that's it. So this is once again the same as the definition of x of e to the j omega. So on the left hand side you have x of e to the j omega plus 2 pi, the right hand side e to the j omega. Therefore the discrete time Fourier transform is a periodic function with a period of 2 pi. Okay, even in fact one more step you can go ahead and you can write as e to the j omega plus 2 pi k. This k can be any number, okay, k, any integer number, 1, 2, 3 like that. Okay, so the end result is x of e to the j omega is a periodic function of period 2 pi. Okay, therefore this strengthens our earlier statement that our range of vision is from minus pi to plus pi. Okay, so in one of the earlier lecture I said that in the digital domain you have to only look at from minus pi to plus pi. This is my range of vision. For digital, but if you take analog, then my range of vision is from minus infinity to plus infinity analog. Therefore it is matching our earlier statement. Okay, therefore we don't have to go beyond that, this range of vision, because it is periodic. Once you know the behavior or characteristic of x of e raised to j omega over one period, then that should be sufficient for me to construct for remaining range. Okay, so one should remember this, that this x of e raised to j omega is a periodic function. And now the next thing one would like to notice is, if you replace x of e to the j omega by minus omega, okay, so if you do that, then the real part does not change because the magnitude is even. So So this I can write x r of e raised to j omega plus j times x j of e raised to j omega, or I can write magnitude of x of e to the j omega, then angle of j times x of, wait a minute, e to the j angle of x of e raised to j omega. This is m of omega e to the j times some phase angle phi of omega. So if you replace omega by minus omega, then this guy is an even function and this guy is an odd function. Similarly, magnitude is an even function and the phase is an odd function. The real part is nothing but the magnitude m of omega multiplied by cos theta of omega, right? Therefore, this real part is even. It's very easy to prove, okay? See, whenever you have two numbers, let's say a plus ib, then what is its magnitude? Mod of r times e to the j times some phase angle theta. Now how do you expand this? Mod of r times cos theta becomes e to the j theta becomes cos theta plus j sin theta. Now replace theta by minus theta. Anyway, the magnitude does not change, mod of r, then cos theta. This is my real part, okay, minus mod of r times sin of theta. If you replace theta by minus theta, let me rewrite one more step so that you can understand in a better way. Replace theta by minus theta, okay, so mod of r cos of minus theta plus j times sin of minus theta, right? Or else it is better to show, instead of this arbitrary example, let me take this example itself so that you can understand in a better way. X of e raised to j omega is equal to m of omega magnitude and e to the j times phi of omega. Now this I can write as m of omega times multiply by cos of phi of omega plus j times sin of phi of omega. Now replace omega by minus omega. So what is going to get? E to the minus j omega is equal to m of minus omega, and here cos of minus phi of omega. Phi of omega is, it's a function, right? So you can take a, minus here, plus j times sin of, it's a phase angle, right? Phase angle is, after all, if you replace omega, then it becomes negative. In fact, you can easily show that it's a odd function, minus phi of omega. Okay, phi of minus omega is equal to minus phi of omega. This you can easily show it, this one. Okay, again this one more step, okay, you can write it, it's not a big deal. So this is, since it is magnitude, then it becomes m of omega multiply cos of minus theta is equal to cos theta, so cos of phi of omega, then this becomes minus, so minus m of omega, then sin of phi of omega. Now look at here, the real part is even, real part does not change, right? This whatever you have here, the same thing here. Similarly, whatever you have here, that will be the same thing is here, but the only thing is the sign is changed. Look at the sign. Okay, sine part. Therefore this imaginary part is odd and real part is even. And one more conclusion one can make is magnitude is even and phase is odd. Okay, therefore the magnitude and the real part are even functions, the imaginary part and the phase, they are odd functions of omega. One also notices that theta of omega or phi of omega, that's how we defined, right? Phi of omega is also periodic with a period 2 pi. Okay. Now if phi of omega, if we increment by 2 pi, neither cosine changes nor sine changes, because phi of omega e to the phi of omega is equal to cos of phi of omega plus j times sine of phi of omega. Now if you increase phi of omega by 2 pi, cos of phi of omega will not change and also sine of phi of omega will not change. Therefore while m of omega can be found uniquely, so as far as m of omega magnitude is concerned, no problem. Okay, so if you increase the phase, if you increase omega by 2 pi or decrease omega by 2 pi, the magnitude will not change. Okay, therefore this m of omega can be found uniquely. Okay, but there will exist a fuzziness or an uncertainty about the actual value for phi of omega. In phi of omega there is a uncertainty or fuzziness, because we don't know the actual phase value if you increase by 2 pi or decrease by 2 pi. For example, suppose if you do the calculation and you got phi of omega is equal to minus 45 degree, it could be 360 minus 45 degree, or it could be 720 minus 45, or minus 360 minus 45, or something like that. So cosine and sine shall make no change. But what about the phase? The phase is different. Okay, minus 45 degrees is different from 360 minus 45 as far as the phase angle is concerned. Therefore about the phase there is an uncertainty. We cannot work with the uncertainty in a laboratory or in a hardware. Therefore we decide once and for all that we will only consider the principal value. Principal value is the value which lies between minus pi to plus pi. Okay, principal value is a value where the phase lies between minus pi to plus pi. We will not consider beyond this range. Okay, now the next thing one would like to ask is, why does one go to frequency domain at all? See, this is so much complex, right? So frequency domain is complex. There is a real part and there is an imaginary part, then magnitude part, phase part. So why does one complicate life? Because it simplifies life in some other fashion. Okay, processing of a signal in the time domain is much more complicated than processing in the frequency domain. Okay, so in the frequency domain processing of a signal is very simple. For example, convolution which requires a multiplication of two signals and then summation, okay, is simply replaced by multiplication. So in the time domain you have a x of n convolved with the h of n, but in the frequency domain it is simply x of e to the j omega multiplied by h of e to the j omega, simple multiplication. So you don't have to do this graphical business and all that. So one goes to the frequency domain, one intentionally complicates life to be able to simplify in some other fashion. Okay, so in the frequency domain, design, analysis or synthesis, everything is much simpler in the frequency domain than in the time domain. So that is the reason we will move on to frequency domain analysis. Okay, now let us take a couple of examples. The simplest example that one could take is x of n is equal to del of n. So by definition, the Fourier transform is x of e to the j omega is equal to summation of x of n e to the minus j omega n, where n goes from minus infinity to plus infinity. So this is a definition. Now this is summation of del of n e to the minus j omega n, and we know that del of n exists only at n is equal to 0. Okay, at n is equal to 0, the del of n value is 1. Therefore in this summation I have only one non-zero value, that is 1 times e to the 0. So this is 1. Therefore if you take discrete time Fourier transform of del of n, then you will get 1. Okay, this double sided arrow, which means that the DTFT is unique. Unique. In other words, if DTFT is given, you should be able to go back to the time domain. If del of n is given, you should be able to go to the frequency domain, and if DTFT is given, if 1 is given, then you should be able to go back to the time domain uniquely, without any confusion, without any ambiguity. Okay, so there should be no arbitrariness, no confusion, no uncertainty. It must be one-to-one representation. It must be one-to-one representation, otherwise it is invalid. And that is why we insisted that phase should be viewed only in the principal domain. Okay, if you don't see the phase in the principal domain, then definitely there will be some ambiguity or uncertainty in the phase, and then there will not be a unique transformation between the time domain and the frequency domain. So whenever you have some uncertainty, we cannot work with that. So the next example that I would like to consider is x of n is equal to 1 over 2 whole to the n u of n. Now by definition, x of e to the j omega is summation of 1 by 2 whole to the n u of n e to the minus j n omega, where n goes from minus infinity to plus infinity. This u of n exists from n is equal to 0 to infinity. Therefore, the summation changes. Summation limit changes. 1 by 2, I can write e to the minus j omega whole to the n. Now you can ask this question, does this summation converge? Okay. If it diverges, then the dt of t does not exist. If it diverges, then dt of t does not exist. So the series must converge. And you can easily say that, okay, e to the minus j omega, you take magnitude, then it is 1. And 1 by 2 whole to the n, it goes to 0 when n goes to infinity. Okay, because the magnitude of e to the minus j omega is 1, and 1 by 2 whole power n, as n goes to infinity, then this guy goes to 0. Therefore, the sum is a finite number. Okay, and the sum is given by 1 divided by 1 minus e to the minus j omega by 2. It's given by infinite sum formula. So use infinite sum formula. Okay, therefore the dt of t does exist. Now e to the minus j omega I can write as cos omega plus j omega. So I can simplify this. 2 divided by 2 minus, right, 2 minus e to the minus j omega, that I can write cos omega, then minus into minus plus, I skipped one step, sin omega, that's it. So this is imaginary and this is real part. So I have numerator and denominator. Now I would like to find out the magnitude and phase of this. So x of e to the j omega magnitude, this is going to be magnitude of the numerator divided by magnitude of the denominator. Divided by magnitude of the denominator. So what is the magnitude of the numerator here? 2, just 2. What is the magnitude of the denominator? Square root of 2 minus cos omega whole squared plus sin squared omega. So this is the magnitude. If you simplify this, 2 divided by a minus b the whole square formula, okay, 2 becomes 4 and cos omega becomes cos square minus 4 times cos omega. So this becomes square root of 5 minus 4 cos omega. If we simplify this, this is the magnitude of x of e to the j omega. Now let us find out the phase angle. Let me call the phase angle theta or phi. Then theta is equal to phase of the numerator minus phase of the denominator. Okay, so in the numerator you have 2. So this 2 I can write as 2 plus j times 0. What is the phase? Tan inverse of imaginary part divided by real part. What is the real part? 2. So tan inverse of 0, 0 degree phase angle in the numerator. What about the denominator? tan inverse of imaginary part sin omega, real part 2 minus cos omega. That's it. So in the numerator 0 degree phase angle, in the denominator this much phase angle I have it. So therefore 0 minus tan inverse of sin omega divided by 2 minus cos omega. Theta is equal to minus tan inverse of sin omega 2 minus cos omega. This is my phase angle and this is the magnitude. So if you look at these expressions, let's say equation 1 and equation 2 very carefully, magnitude is maximum when cos omega is equal to 1. Right? You want the denominator as small as possible. So the maximum occurs from 1, the maximum occurs at omega is equal to 0. Therefore, maximum of x of e to the j omega occurs when omega is equal to 0, and that maximum value is 2 divided by square root of 5 minus 4. So that is 2. Okay, so that is the maximum value. So what is the minimum value? So the minimum occurs when omega is equal to plus or minus pi. Plus or minus pi. So this becomes 2 divided by square root of 5 minus 4 times cos of pi. Cos pi is minus 1, minus times minus plus, 5 plus 4, 9. So 2 by square root of 9, that is 2 by 3. Okay, so this 2 by 3 is going to be 0.6667 and keep on goes. It's a recurring number. So whenever you have like this, then don't convert to like this. Okay, just keep it as 2 by 3 as it is, especially in digital signal processing. Okay, so the maximum value is 2 and the minimum value is 2 by 3. Now what can you say about the phase? The phase is theta is equal to minus tan inverse of sin omega divided by 2 minus cos omega. Now what is the phase at omega is equal to 0? Phase equal to 0. So the phase starts from 0 at omega is equal to 0. Okay. So, and moreover, as I said, the magnitude is periodic. It is obvious, right? The range of vision is minus pi to plus pi. If you try to plot the magnitude m of omega, the maximum value is 2. At pi, it is 2 by 3. Okay, it slowly goes like this. Maybe I can put like this, like that, 1 2 3, then okay, like this, and again 1 2 3, it goes like this. One second. Oh my god, it goes, then 1 2 3, this point it goes. So this is pi and that one is 2 pi and this one is 3 pi and this point is minus pi, 1 2 3, this point, like that, 1 2 3, okay, this point, like this, and this one is minus 2 pi, minus 3 pi. Therefore the magnitude is periodic. It is obvious, and the range of vision is minus pi to plus pi. In fact, if you plot from 0 to pi, that is good enough, because minus pi to 0, it is an even function, right? Once you know the behavior of this function from 0 to pi, then that is more than enough for me to determine the left hand side also, because it is an even function. Therefore, I can construct once I know the function from 0 to pi. So we will basically confine 0 to pi, and if you look at 0 to pi range, what can you say about the function of the signal? It is monotonically decreasing. Monotonically decreasing. So this is one observation that you can look at from the magnitude plot. Okay, therefore the signal, given signals 1 by 2 whole power n u of n reaches low frequencies. Okay, is reaching low frequencies. At 0 frequency it is maximum, and then it gradually goes down. Okay, now let us look at the phase plot. So as I said, at omega is equal to 0, the phase angle is 0. So you can substitute different values of omega and you can get the values, and you can take it as an exercise. So it is like this. And it's an even function, right? Like that. So this point is omega is equal to 0, and this one is theta of omega, and this is your omega. So it is a sinusoidal, it is slanted sinusoidal. It is a slanted sinusoidal. So it can be of any arbitrary shape, but there is a maximum and there is a minimum. Again in phase we can find minus pi to plus pi. So where is pi? This point is pi, and this point is minus pi. Since we know the phase is an odd function of frequency, we simply plot from 0 to pi. Once you know to 0 to pi, then negative of that will be the 0 to minus pi. Okay, so and we removed all uncertainty by confining the phase angle between minus pi to plus pi. Fortunately, here the maximum does not go beyond the 0.5 radians. Okay, so that's it about the magnitude plot and the phase plot of the second example. Okay, now let's come back to the definition of DTFT. What is the definition? X of e to the j omega is given by summation of x of n e to the minus j omega n, or n omega. So I have already made the point that if the DTFT is to be of any use, then it must be unique. Okay, for a given signal, the DTFT must be unique. I cannot get two DTFTs. Okay, x of n is given. I should get only one answer. I should not get two answers. Then your DTFT is not valid. Okay, so that means 1 to 1. I should get 1 to 1 result. It must be unique and 1 to 1. That is, given x of n, you should be able to find capital X of j omega, e to the j omega. Okay, so there cannot be two answers. Okay, so even if you get two answers, then one will be wrong and one will be correct. Okay, if there are two answers, one will get full mark and the other will get 0 mark. Okay, so one will be right, the other will be wrong. So if you don't do it properly, then both may be wrong. But one can arrive at the correct answer. That answer is unique. It cannot be expressed in any other forms. In a similar manner, if the signal is given in the frequency domain, see x of n is given, you can get x of e raised to j omega. Now if somebody comes and gives you x of e to the j omega, then you will be able to find x of n. Okay, you should be able to go back to x of n. Okay, you should be able to go back to the time domain. See, time domain to frequency domain, I can go by using dt of t. If somebody gives an expression in the frequency domain, then I should be able to go back to time domain using inverse discrete time Fourier transform. Okay, so inverse discrete time Fourier transform. Okay, now if you look at this definition, let me call equation number 1. You recall what Fourier series was. It looks like a Fourier series, right? But it is not exactly Fourier series, but it is in the frequency domain Fourier series. Recall the definition of Fourier series. Okay, and this one is periodic with period 2 pi, and it is expressed in the sum of exponentials. Okay, sum of exponentials with the coefficient x of n. See, you have like this summation of e to the minus j n omega, and what is the, instead of ak or bk or ck, I have the coefficients x of n. So instead of ak, I have x of n. Instead of e to the minus j n omega, here also I have e to the minus j n omega. Therefore, in this case, how can I get back x of n? X of n must be given by the following formula for evaluation of Fourier coefficients. Recall the Fourier coefficients formula, AK formula. What is AK formula? AK is equal to 1 by 2 pi integral of minus pi to plus pi, right? X of t e to the minus j omega t times dt. Remember this formula. Similarly, here also we are going to get x of n 1 over 2 pi integral of x of e to the j omega n and d omega. Okay, instead of t, here I have omega, and my range of vision is minus pi to plus pi. Let me call this is equation number 2 and this is equation number 1. This is dt of t and this one is I dt of t, inverse discrete time Fourier transform. Okay, these are the two pairs, and the equation 2 is the inverse discrete time Fourier transform relationship. Now equations 1 and 2 are not independent. Very, very important point. Okay, they are not independent of each other. So this is another point I want to make very clearly and very loudly. Equations 1 and 2 are not independent of each other because they require one-to-one transformation. In other words, if equation 1 is given, then equation 2 can be derived, or if equation 2 is given, then equation 1 can be derived. So both are not a matter of definition. Only one of them can be defined as the definition. Only one of them can be defined. The other should follow. If one is given, the other can be derived. Okay. In other words, if I start from equation 1, then I should be able to derive equation 2. Or if I start from equation 2, then I should be able to derive equation 1. And the derivation is extremely simple. Okay. So what you do is substitute take equation 2, x of n is equal to 1 by 2 pi integral of x of e to the j omega n d omega. See, this is my equation 2, right? Now what you do is substitute for this guy. Okay. Start from here. What is x of j omega from equation 1? This is 1 by 2 pi integral of summation of x of n e to the minus j omega n and then e to the j omega n and d omega, where n is going from minus infinity to plus infinity. Now there is a small confusion here. Here also n and here also n and here also n. And this n corresponds to this integration. And this n corresponds to this summation. This n corresponds to this summation. So there will be some confusion. So therefore you cannot use n in both the places. Okay. So what you do is, to remove this ambiguity, you do like this: 1 by 2 pi summation of, instead of writing n, then you replace m is equal to minus infinity to plus infinity x of m e to the minus j omega m and then e to the j omega n d omega. Now this m corresponds to this summation and this n corresponds to this integration. Okay. Therefore the trick is, you cannot retain n in both the places. Okay. So if you substitute for x of e to the j omega, you cannot retain small m because the summation and the integration are independent of each other. The integration contains j omega n and the summation contains e to the minus j omega n. Look at here. Okay. If you look at here, it contains e to the minus j omega n. So I cannot write n in both places. So you must change the dummy variable. You must change this dummy variable to m. Now this x of m is independent of the integration. So I can pull out of the integration. So 1 over 2 pi integral of x of m summation of, you combine these two exponentials, e to the j omega times n minus omega d omega, and the limit is minus pi to plus pi. Hold on, I can still reduce this. Okay. And these two things I can pull out of the, what am I doing? Oh, I'm sorry, I did a blunder. I'm very sorry. So this summation and these two guys independent of the integration. So I can pull out of the integration. Therefore summation of x of m, where m goes from minus infinity to plus infinity, and then integral of minus pi to plus pi. You put 1 by 2 pi here. And as you know, this function consists of cosine and sine term, this one. Okay. So by one period the cosine will become 0. So the integration of sine will also become 0, except in the case n is equal to m. Okay, so this is very important step in order to simplify this. So this I can write as cos of omega times n minus m, right? This is m. N minus m times omega plus j times sine of n minus omega, n minus m times omega. Okay, and this is cos term and this is sine term, and you are integrating from minus pi to plus pi, and here also you are integrating from minus pi to plus pi. So over an integer number of cycles, the area will be 0. In case if you take a cos function like this, if you integrate from minus pi to plus pi, hold on one second, sorry, this is n minus m times, this is n minus m times omega. Now this, cosine and sine, if you do the integration over one period, the cosine will become 0, integral of sine will also become 0, except in the case when n is equal to m. When n is equal to m, in this expression you substitute n is equal to m, only one value. Okay, so in this summation it has so many values, right? This summation has m is equal to minus infinity dot dot dot, then m is equal to n, let's say, one second, it has 0, 1, 2 up to n minus 1, n plus 1, comma up to infinity. Okay, therefore this summation takes minus infinity to plus infinity. Among this infinite number of values, only one value exists. What is that value? M is equal to n. So in this summation I am going to take only one, even though it has infinite number of values, like I have x of minus infinity, then dot dot dot, x of 0, x of 1, x of 2, dot dot dot, x of n minus 1, x of n, x of n plus 1, dot dot dot, then x of infinity. But among this infinite number of values, I have only one non-zero value. For rest of the things, this integration becomes 0. The integration is non-zero only when n is equal to m. Okay, therefore this summation is going to be, therefore this summation is going to be give only one value, that value is x of n times 1 by 2 pi, only one value. What is that only one value? E to the j omega of n is equal to m minus m 0 times d omega, and minus pi to plus pi. Okay, so this is x of n 1 or 2 pi. If we carry out this integration, then this will becomes 1 by 2 pi times 2 pi, 2 pi will get cancelled. So on the right hand side x of n. What about the left hand side? Left hand side we started with x of n. So on the left hand side I have x of n, in the right hand side I have x of n, proved. So that is the way you prove that the right hand side is equal to the left hand side, and which is equal to x of n. So the derivation is simple. So that, okay, so you can simply try this. Okay, so I think let me stop at this point. Before concluding this lecture, let me give the summary. So in this lecture we started with discrete time Fourier transform, and one can ask a question: why do you go to DTFT, discrete time Fourier transform? To make life more complex, because see, the DTFT makes life more complex, but even though we would like to use the DTFT, why? Because analysis, synthesis and design become much simpler. In frequency domain. So that is the reason we would like to move on to frequency domain. But in frequency domain, one has to be handled with care. Okay, one should be very careful because of uncertainty in the feed domain. In the feed domain, there is uncertainty. To overcome this uncertainty, you should only always look at the principal domain minus pi to plus pi. Don't look beyond this minus pi to plus pi. But there is no uncertainty in magnitude, but theta can be multi-valued because addition or subtraction of 2 pi doesn't matter. And the other point is that I make is that in the DTFT relationship, DTFT and inverse discrete time Fourier transform are not independent of each other. One depends on the other. It has to be, right? So to any engineer it has to be useful, then the transformation must be unique. That is given one, you can find the other. Okay, so one is a matter of definition, the other the forward transform or the reverse transform, the other one should follow it. So how did you find the inverse discrete time Fourier transform? By comparing the Fourier series. That was also somewhat unconventional, but the Fourier series usually is written as a periodic function in time. Okay, and but here we used in the frequency domain. Here we wrote a periodic function in the frequency domain. Generally, if you take the definition of Fourier series, where we use a time domain, but here we used in the frequency domain. It was not difficult for us to find out what the inverse discrete time Fourier transform is. Okay, so I think this is a time where I can stop this lecture. Thank you very much.